Welcome to Medicos. Have you ever wondered how your muscles know when to move and how much force to use? Whether it's the fine control needed to move your eyes or the powerful contractions to maintain your posture, your body relies on an intricate system of motor units and muscle sensors. But how does it all work? Understanding the complexities of muscle control can be overwhelming, especially when you dive into terms like motor units, muscle spindles, and Golgi tendon organs. But don't worry, this video breaks it down into simple terms so you can easily grasp the science behind your muscle movements. Muscles are the bundles of fibers designed to contract and relax, creating movement in every part of your body. They're like tiny motors strategically placed throughout your body, working tirelessly to power your every move. Each muscle fiber is a powerhouse, converting energy into motion. But here's the thing, muscles don't act alone. They are part of a complex system that includes your nervous system, which sends signals to your muscles, telling them when and how to move. This system includes your brain, spinal cord, and a network of nerves communicating with your muscles. Whether you're lifting weights, sprinting, or simply typing on a keyboard, your motor units and muscle sensors are hard at work. They constantly monitor and adjust your muscle activity to match the demands of your actions. And when your muscles get tired, these sensors help manage fatigue and recovery, ensuring you can keep going. Let's start with the basics. Motor units. Picture this, a group of muscle fibers, all fired up and ready to contract, controlled by a single nerve cell called a motoneuron. Each muscle fiber in this group is ready to spring into action at a moment's notice, responding to the motoneuron's command. When the motoneuron sends a signal, the entire team springs into action, generating force and producing movement. The more motor units recruited, the stronger the contraction. When you need to lift something heavy or sprint quickly, your body calls upon more motor units, increasing the force and power of your muscles. This teamwork within our muscles is what allows us to perform a wide range of physical activities, from delicate tasks like writing to powerful actions like lifting weights. Understanding motor units helps us appreciate the incredible coordination and strength of our muscular system. Now let's talk about the motoneuron pool. It's like a gathering of all the motoneurons responsible for controlling a particular muscle. But not all motoneurons are created equal. Some are small and mighty, while others are large and in charge. This brings us to the size principle, a fundamental concept in muscle physiology. The size principle states that smaller motoneurons are recruited first, followed by larger ones as the demand for force increases. So what's the deal with small and large motoneurons? Why the size difference? Well, it all comes down to the type of muscle fibers they control. Small motoneurons innervate slow-twitch fibers, which are fatigue-resistant and perfect for sustained activities like maintaining posture. Large motoneurons, on the other hand, control fast-twitch fibers, which are powerful but tire quickly. They're the sprinters, built for short bursts of intense activity. By recruiting different types of motor units, your body can fine-tune muscle contractions for optimal performance in various tasks. Section 5, muscle sensors, your body's built-in feedback system. Your muscles have a built-in feedback system, muscle sensors. These specialized sensory receptors provide your brain with constant information about muscle length, tension, and the position of your joints. Section 6, extrafusal versus intrafusal muscle fibers with different jobs. Not all muscle fibers are created equal when it comes to sensing. We have two main types, extrafusal and intrafusal fibers. Extrafusal fibers are the heavy lifters, responsible for generating force and movement. Intrafusal fibers, on the other hand, are nestled within specialized sensory organs called muscle spindles. They're like the brains of the operation, detecting changes in muscle length and sending this information back to the brain. Section 7, muscle spindles, detecting stretch and keeping you balanced. These tiny spindle-shaped organs are scattered throughout your muscles, acting like miniature sensors. When a muscle stretches, so do the muscle spindles within it. This stretching activates sensory neurons within the spindles, which send signals to the spinal cord, providing your brain with real-time information about muscle length. This information is crucial for maintaining balance, coordinating movements, and protecting your muscles from overstretching. Section 8, nuclear bag versus nuclear chain dynamic duo of muscle sensing. Within each muscle spindle, we have two types of intrafusal fibers, nuclear bag fibers and nuclear chain fibers. These fibers work together to provide our muscles with the necessary feedback to maintain balance and coordination. They're like the dynamic duo of muscle sensing, each with its own specialty. Nuclear bag fibers are highly sensitive to changes in muscle length, especially rapid stretches. They are the first responders, always on high alert to detect any sudden changes in muscle length. They're like the alarm system, quickly detecting any sudden movements. This rapid detection is crucial for activities that require quick reflexes, such as catching a falling object or dodging an obstacle. Nuclear chain fibers, on the other hand, provide information about the static length of a muscle, ensuring that our muscles maintain a steady state even when we're not moving. They're like the steady hand, constantly monitoring muscle length even when it's not changing rapidly. This constant monitoring helps us maintain posture and perform tasks that require precision and stability, like writing or playing a musical instrument. Together, nuclear bag and nuclear chain fibers create a comprehensive feedback loop that integrates with our nervous system. This loop allows our body to make real-time adjustments, ensuring smooth and coordinated movements, whether it's the dynamic sensing of rapid movements or the static monitoring of muscle length. The dynamic duo of muscle sensing plays a vital role in our everyday activities. Their seamless collaboration keeps us balanced, coordinated, and ready for action. Section 9. Muscle spindle reflexes, lightning-fast reactions to keep you safe. Muscle spindles play a crucial role in muscle spindle reflexes, lightning-fast reactions that help protect your muscles from injury. Imagine you're walking and accidentally trip over a curb. Your calf muscle suddenly stretches, activating the muscle spindles within it. These spindles send signals to the spinal cord, triggering a reflex arc that causes your calf muscle to contract and prevent you from falling. It's like a built-in safety net, always there to catch you when you least expect it. Section 10. Gamma motoneurons, fine-tuning muscle spindle sensitivity. Now, here's where it gets really cool. Your nervous system can actually adjust the sensitivity of muscle spindles through gamma motoneurons. These specialized neurons control the tension of intrafusal fibers within muscle spindles, fine-tuning their sensitivity to stretch. It's like adjusting the tension of a guitar string, ensuring the muscle spindles are always perfectly tuned to detect even the slightest changes in muscle length. Section 11, the grand finale, motor units and sensors working in perfect harmony. As we've seen, motor units and muscle sensors work together in perfect harmony to control muscle movement and posture. Motor units provide the power, while muscle sensors provide the feedback, ensuring your movements are smooth, coordinated, and precise. It's a remarkable example of the intricate design of the human body, where every component plays a crucial role in keeping us moving and grooving. Section 12. Keep exploring, keep asking questions, and keep marveling at the wonders of your own body. And remember, stay curious.